So at some point, there is a transition when the degeneracy kicks in the evolution from the main sequence to the subgiant branch as the star is passing from the subgiant branch to the red giant branch. You can define based on the pressure equation of state when this degenerate pressure becomes stronger than the thermal pressure. And that is this line here. This red line is the transition between ideal gas and degenerate. As you see, it happens somewhere in the transition to the red giant branch. That's the transition that happened in the core. The core was contracting and heating up, and at some point the density is so high that it goes degenerate. So what happens in an ideal gas as you have this contraction? You contract, the temperature rises, the pressure also rises. If the temperature falls, the pressure falls. So if you have a radiative loss, that means that the temperature goes down, you have cooling, you have less support against gravity, and then contraction. So the core keeps contracting as it's trying to generate more pressure to equilibrate against gravity. A core of degenerate matter is stable because the pressure depends only on the density. If the temperature is rising or if the temperature is falling, the pressure couldn't care less. So you can continue having radiative losses indefinitely. The degenerate core is stable. You have all this gravity compressing on the core. All the core needs to do to match it is to reach a density where it matches by hydrostatic equilibrium the weight of the outer layers. So you equilibrate the gravity with this pressure. In the ideal gas, that is never going to happen because you keep losing energy, you keep irradiating, and then the temperature falls and you must keep contracting to reach a new state of equilibrium to equilibrate gravity. Because the degenerate equation of state does not depend on the temperature, radiative losses can continue indefinitely. As you saw, this pressure here exists even at absolute zero. So the degenerate core is stable. However, at this point 7 here, the tip of the red giant branch, temperature and density have become so high in the core that you ignite the triple alpha reaction. The triple alpha is the mechanism by which helium burns and generates carbon. You have helium combining with another helium-4. You have helium-4 combined with another helium-4. It generates beryllium-8. Now, beryllium-8, it's a very short-lived nuclide, but it has a lifetime, which is about the time that two particles moving in the core will take to collide with each other. So it has enough time, even though it's short-lived, to collide with another helium-4 and then generate carbon. So this is the process that leads to carbon production. This is the process of helium fusion. At the point of the red giant branch here, that's when helium fusion starts. But we are in a situation where the core is degenerate and the pressure does not depend on the temperature. So let's see what would happen if you reach the helium burning under non-degenerate, under normal conditions. What you have is that the nuclear reaction starts. You start burning helium. The temperature increase due to the nuclear reactions will lead to an increase in the pressure. The pressure leads to expansion. But expansion in turn leads to cooling. So cooling lowers the rate of nuclear reactions. Cooling would lead to contraction, which then heats up. So you have a thermostat here. If you try to heat, you end up cooling. And if you try to cool, you end up heating. So this is controlled. You have a thermostat built in. It keeps the nuclear reactions tuned. You basically have controlled fusion. That's what happened in an ideal gas. If, on the other hand, fusion happens in the degenerate gas, it changes altogether. You have that as the nuclear reactions increase the temperature, nuclear reactions lead to heating. The heating has no bearing on the pressure because the pressure depends only on the density. The temperature increases, which increases the rate of nuclear burning, and in turn increases the temperature even further. The star is not expanding, it's not cooling down. So you produce heating. The heating leads to more nuclear burning. That leads to even more heating. And the process runs away. There is no thermostat. More nuclear burning, more heating, more nuclear burning, more heating, the process runs away. You basically have a runaway fusion. A degenerate core of helium that ignites triple alpha is a bomb ready to explode. And this is known as the helium flash. The helium flash generates about 10 to the 48 erg of energy. That's an incredible amount of energy. That's the energy that the sun would generate in 10 million years. It's about 100 billion times the solar output in just a few seconds. Yet, the vast majority of this energy is used to lift the degeneracy, basically to melt the core back into an ideal gas, and nothing is seen from the outside. Helium then burns steadily in a core of ideal gas.